electric field, and then develop both directivity and gain. And I want to tell you one other thing about this. A lot of the stuff that we've done, where I was trying to bring you up to speed with the basic theory, people are going to wonder, well, what will I test on? I'm not going to test you on that. I just want to be clear. This is a class that's based on applications. So I want to make sure you know that. And now, I got a few things. What I want to try to do this is efficiently, quickly, but I don't want to move in a way too fast so you don't understand, appreciate what I'm saying. In Dr. Wentworth's book, all the wire antennas are assumed oriented on the z-axis. And generally speaking, they're gap driven. By that, it means if we have an antenna of length L, there's going to be a plus to minus voltage here. I hope you can appreciate it. I'm trying to show you an antenna right here. That would be a gap drive that would cause a current I here. Are you all with me on that? That's just like we've been talking about. Now, this is located at the origin, and we are always in spherical coordinates. The angle theta is always measured from the z-axis. He always is going to use an XYZ reference frame, and then he'll go to spherical coordinates. In the book, he uses small r. I write large R because my small r look like V's. That's the only reason. Do y'all follow me? Nothing here other than trying to clarify with the large R. This gives rise to an electric field, and it's actually in the theta direction. And here's what I mean by that, because I think this question's coming up. If I want to know what direction the electric field is anywhere, if I move down this way, you see the way this marker's pointing? Can you all see that? It doesn't matter if it's out this way, it's always in a direction that's perpendicular to the radius vector r, and it's along a trajectory that would run from the North Pole here down to the South Pole. That's the best I can do. Y'all follow me? It's in the theta direction, and A theta is this way. So E would be equal to J eta beta times I times the length L of the antenna. And this will be for a short dipole. Then it's going to be divided by 4 pi r. Now there are different formulas. I'm going to show you another one in a second. All have the same essence. They always will give you the same values, but there's different forms of this. Then it's going to vary as the sine of the angle theta, and it will be times e to the minus j beta r, a theta. Now, the things to get from this for the electric field is, and this is in the far field, by the way, is that it varies as the sine of this angle, which means the electric field straight up and straight down at theta equals 0, or theta equals pi, 180 degrees is 0. Y'all follow me? And the thing you take from that, dipole antennas never radiate up and down their axis. They have a maximum radiation pattern perpendicular to their axis. Do y'all follow me? Now, it varies as 1 over r, and it's proportional to I. That's basically what you gleaned from this. The J term means the phase is 90 degrees, but that's kind of a abstract concept. This is a steady frequency. That doesn't mean much. Y'all follow me on this? All right, now if we want the H field, since we're in the far field, we just take E in the theta direction and divide it by eta. And eta is 120 pi ohms, or about 377 ohms. It's just that of free space, the ratio of E to H. And it would be in the A phi direction. Now, I want to do this one time. If you think about power density, first of all, this is what I did last time. I got hung up at some of the math. I should have spent a little more time on it. If you talk about the average power density, I got to mention this. Most of the time, and if you're working in places like Huntsville, the Arsenal, or for NASA, something like this, you're going to see something that's termed the pointing vector. He doesn't mention it yet. The pointing vector is just usually given as S. Now, it is the power density with a vector direction. This is 1/2 the real part of E cross H conjugated. So this is, that pointing vector is in fact what Dr. Whitmore's book calls P average. And for us in the far field, it will be 1/2 the magnitude of the E field squared over eta in the AR direction. Do y'all follow me on that? I want to make sure I introduce this symbol S. It's used throughout the literature, and some of you will see this and you'll wonder what it means. It's just called a pointing vector. Why they use that S, I don't know. They just did. It's the same thing as P average. The units of this are watts per meter squared. I'm going to mention something about this. So last time when I was talking about this, I said, well, P av is really 1/2 magnitude of E squared over eta in the AR direction. Do y'all remember that? This is for any propagating wave, isn't it, class? If it's propagating, launched plane waves will have this effect. Well, I'm going to mention something. You don't need to write this down yet, but I'm just going to show you. This is in his book. If we did this, we'd see we have 1/2. Then E squared would be simply eta beta Li right there over 4 pi r times the sine squared. I'm going to break that outside. And it would be in the AR direction divided by eta. Now the reason I did that, I wanted to just show you that that's the E field. I'm taking all the constant terms basically, squaring it, breaking out the sign, and getting rid of this phase term, because when we take the conjugate of it right here, cross product, it clobbers the E to the J business. Do y'all follow me? There is no phase with power there. When you do this, you can see that the actual average power density right here will be equal to, well, got an eta squared eta, and 4 pi I have 1/2, then I have eta, then I have beta squared, then I have L squared, I squared, over 4 pi squared, R squared, sine squared, theta.
How did you get?
Come over here. What?
How did you get the sine squared at P? Oh, I see. I see
Because
it now.
E field varies as sine. You square it, you get a sine squared. That's it.
I see it now.
Or if you want to do E cross H conjugate, both E and H vary as sine theta, you get a sine squared. All right, now this, if you take this, and you simply replace beta by 2 pi over lambda, and then eta by 120 pi, now you get P ab here equal to 1/2, and this is 120 pi over 4 pi squared. Beta becomes 2 pi over lambda squared. Then you get L squared, I squared, over R squared, sine squared theta, in the AR direction. Now I'm going to get to the really bottom line. This is where I was. I think I got about there last time, and I got tangled up. So here we go. Hopefully nothing is going to happen. I want to just say this. Look at this. You don't have to know this right now. Just trying to show you how I got it. All right. What they usually like doing is grouping L over lambda squared. It's a ratio of length to lambda. So I'm going to do this. Down here, I'm going to say average power density is going to be proportional to L over lambda squared. They're both squared. Huh? I know it's proportional to I squared. That's this. Proportional to sine squared. And inversely proportional to R squared. The reason I did that is everything left I'm going to manipulate. You with me, class? Everything up there that's left. So I'm going to erase everything that's left, or I'm going to erase this stuff from here, in the AR direction, by the way. And I'm going to find that constant, so I get rid of that, and that. Y'all with me? I just want to find out what that thing comes down to. Last time I said, well, I got a pi squared and a pi squared, so I can get rid of the pi squared. Do you agree with that? Now I have 4 squared, but that's 4, so I get rid of this. With me? Now I take a look at what's left. Here I have 2 in the 120, that's 60, right? 60 by 4 is 15, 15 pi. That's the one thing I was trying to do. Now the reason I like this formula instead of Whitmer's form is this. Remember, for this to work, L has to be less than 1/10 of a wavelength. Y'all with me? So if you have wavelength, and you know length, this is a ratio squared. It's manageable. A lot of times the length is like 0.001 inches, something very small. But if it's a ratio of the two, it becomes more in line with something. Squaring won't just, make the dot zzz as a whole bunch of zeros. It'll be manageable. The I squared really brings out is proportional to square of I, inversely proportional to square of the distance, directly proportional to sine. With me, class? Now I want to do that. This is for the short dipole that is so important. Now, it's a lot of different small antennas that all have the same type of sine squared pattern. I want to just mention one other thing about this one. Last time we did this where we took this power density right there, that's in watts per meter squared, and we integrated over an entire surface. Do y'all remember this? Remember that? We got the radiation resistance for antenna. How many remember that, class? I didn't give you any real homework to chew on about this. You're going to get a bunch tonight. So for the short dipole, write this down. And this again is for L less than lambda over 10. We can view that thing as really a resistor with a radiation resistance. As such, and we can say the total radiated power from this is equal to 1/2 I magnitude of I squared R rad, and the radiation resistance, and this is for the short dipole, and I'll get out of your way, is equal to 80 pi squared L over lambda squared, and it's usually small. The units of this are ohms. Now here's where we're going with this. You haven't seen this yet. If I know for a given antenna that this is the radiation resistance if it's short, I can figure out for a given voltage how much power is radiated. Y'all, I can figure out how much current flows, right? If you know the radiation resistance, and theoretically now, you would take that and divide it into the voltage, you get the current. You with me on that, everybody? You got the current, you can find the power radiated, right? You got the current, you can also find the E field, can't you? See how it's proportional? Anyway, you can find the H field, and you can find the power density. Now comes the shortcut ways of using it. We're going to attach a figure of merit to antenna performance, where we're going to talk about their ability to focus. I just touched on that briefly. It's called directivity. And I'm going to erase this, put it down for a reason though. So, how many have heard of directivity or gain of antennas? Anybody? Yeah? In your own words, what does that mean? You can.
I just remember reading about it in the book, and they had a section where they have a graph, and so the directivity is where you have the largest. It transmits the best.
Here's what it really is. You're going to see that they compare everything to an isotropic radiation system. Now, isotropic radiation is just radiation at the same level, the same power density in all directions. A good example is the sun. If you look at the sun, no matter where you are, generally, it has the same power density, or same illumination, same amount of watts per meter squared. Y'all follow me? A candle's not bad either, all right? But antennas aren't like that. However, what we like to do is get a figure of merit to how much better or worse a certain antenna is compared to an isotropic. So we need something we compare its performance to. You with me on this? So, in general, this is called directivity. Let me get a different marker. And I got to tell you one other thing. I'm going to show you how to calculate this in a second. But it's more important that you appreciate what it does for us. So when we talk about directivity, the symbol is D. Go figure. All right, the problem with D is it means diameter too. And when we have dish antennas, oftentimes if you see D listed next to a dish antenna that you're selecting from a catalog, that might be the diameter. You got to look at the units. D is unitless. Y'all follow me? Diameter will have inches, centimeters, meters, something like that. All right, so this is the symbol they use. And directivity is never a function of R, but it can be a function, and it is usually, of theta or phi or both. Now that's important. So, what does directivity do for you first? Let me just tell you what it is. The actual directivity of an antenna is the ratio of the average power density for a given, and by the way, range will cancel out of these things. The average power density at a given range, theta, and phi. So the power density that occurs from the antenna you got divided by the average power density that would occur if the antenna was isotropic. All right? Well, I don't want to spend a lot of time on this. Well, what would the average power density be for something if it's isotropic? That would be the total radiated power, right? Over 4 pi r squared. Do you all agree with this? Think about it. I got 50 watts, and they're uniformly distributed over any spherical surface, radiating outward. So 50 watts, what's the spherical surface? 4 pi r squared, right? That would be how many watts per square meter. Does that make sense to everybody, class? Right? If you look and think about it rationally, it's saying the same amount in every direction at any given angle, theta and phi, it doesn't matter. This would be in the AR direction. It would be watts per meter squared. Well, what is this? Well, that we have to calculate. I put up that thing there, right? No matter what you do, you're going to find out something. R here cancels R here. So it's just as easy to set R equal to 1 and forget about it. I'm telling you that right now. But here's really how we get directivity. Since it's a ratio of the average power density over the power density that would occur if the antenna was isotropically radiating that power, what it actually comes down to is this. Write this down. It'll be 4 pi divided by, and I'm going to put this in here, divided by an integration. And this is over the entire surface of a sphere from 0 to pi, from 0 to 2 pi, of what Dr. Wentworth calls the normalized power density, and I'll get to that, times the sine of theta, d theta, d phi. Now this might seem a little foreign, but I got to make mention of this. I got to tell you. You see how I said this is the average for isotropic? Just look at this for a second, right? Let me just back up and just show you something. Well, directivity average power density is P rad over 4 pi r squared. Up here, there's going to be some way for me to get P rad and put it into the actual parameters that have to do with beta, I, L, and all that. In other words, rearrange things. There'll be a P rad here, but there will also be a function of theta and phi up here, and it will actually fall off as 1 over r squared. Do you notice all power falls off as 1 over r squared from the singular source? If it's propagating, it has to. I'm talking about a finite source if you get far enough away. This is the power density. The r squareds will go away, I promise you. You see that 4 pi will come upstairs, the p rads will cancel. But that explains at least the 4 pi. I used to go through this whole proof. Dr. Wentworth tries to. It never really seems to matter to students. They want to see it applied. So what is this? PN is, write this down, this is in his book, is normalized power density. So what does that mean? When I say something's normalized, what does it mean to you?
Orthogonal, like a unit vector.
I have to, normalization usually means that the peak value is 1. Like, that's usually, it's normalized means it's ratio to something, and when it's, in our case, when something's normalized, it means the maximum value of this power density can be 1. Y'all follow me on that, class? Now let me just give you an example. You saw already, you don't have to write this down, but just think about it. I said for the power density from an antenna, a short dipole, we found out that the average power density was equal to 15 pi I squared. You don't need to write it down. L over, L over lambda squared times sine squared of theta over r squared. Remember we did that? All right. What does it normalized mean? It means P normalized of theta and phi would be the maximum value of that. All right, I'm sorry. It would be the actual. It would be the actual value of PF, my bad, over PF max. Now, I gotta make sure you see this because this will confuse you if you don't hear me. This thing's only a function of angles. Do y'all see this right here? Not a function of R, not a function of current, not a function of. What value of angle makes this a maximum? Sine equals theta 90 degrees or pi over 2. Do y'all see that, class? The sine of that would be 1. What it's really saying is the maximum value is just that. If we divide it into this, we find that the normalized power density for this waveform is sine squared theta. Do y'all follow me? How many see that right there? Makes sense, normalization? Now, if that wasn't a sine, if it was cosine squared, then what would the normalized power density be? Suppose this was all that, only it's cosine squared. What would the normalized power density be then? Just the cosine. Y'all follow me? If this was cosine, you don't have to think cosine squared, I should say. Then down here, the peak value would still be all that, right? The cosine's peak value is 1. Y'all agree with that? We just divide out everything, all that stuff into this, and we'd be left with cosine. I'm trying to make the point. Now, it is possible, theoretically, to have an angular function, all right, that would be greater than 1, right? You could have 1 plus cosine theta squared. Y'all follow me? And then you would still have to find out what the maximum value of that function is and divide that maximum value into the actual remainder there, I mean, whatever form it takes to get the normalized. But the key thing here is, for ours, when it's sine, it shows you how the actual power varies in angle. Do y'all see that? You get rid of the peak, the only thing you care about is the signature, the normalization. All right, now that is used here. I want to take a moment and explain something. Remember how I said you're going to see that sine cubed integral over and over again? How many do? Do you remember me doing it? Look what happens here. Sine squared sine cubed. Another thing that can happen here can be cosine squared sine theta. That's the easier one. Because then you got u du right there. So if we take this as the normalized, when we have a short dipole, you can write this down. Then you can say the directivity of a short dipole. And I want to make one point here. For this particular thing, this would be the maximum directivity. So put down max here. This is the value of the max. I'll show you how to get the general angular value. So this is d max. And that's equal to 4 pi divided by the integral from 0 to 2 pi, the integral from 0 to pi of sine squared of theta times the sine of theta d theta d phi. Now remember last time I said this is really a sine cubed, right? Do you remember, I mean, really it's sine cubed, but the way we did it was what? We had sine squared and we used 1 minus cosine squared. How many of you remember that? Sure. I took sine squared and made it 1 minus cosine squared. I'll just do it for a second and show you the results. When I make this 1 minus cosine squared theta times this, y'all see now if u is equal to cosine theta, du is minus sine theta d theta. Just a show of hands. I'm not going to, keep on going over this. But are you with me on this, class? So this is a u du. The integral of d phi from 0 to 2 pi is just 2 pi, right? And do you remember what the integral of that sine cubed d theta was from 0 to pi? Anybody?
4/3.
4/3, and that's going to be something that comes back at you over and over again. So what this amounts to is this is 4 pi, all right, divided by 2 pi times 4/3. Or, 4's cancel, pi's cancel, you can see it's 3/2 or 1.5. Now, this is true for all small short dipoles. The directivity maximum will always be 1.5. So for a short dipole, it's 1.5. That's not quite the whole story with directivity. I want to make sure you see this example. That's the maximum, right? So how do you get the directivity at any angle? So you know, if you had that directivity and you had the total power radiated, you could get the power density, and I'm going to do that next. Here's how you do it. You say that the I probably should put it right here. This is a little out of order, but you can say D as a function of theta and phi, and this is true in general, is D max for that antenna times the normalized power density of the antenna. So for our short dipole, what happens is, this is for the short dipole only. You find that D as a function of theta and phi is 1.5 sine squared theta. Ready? Now that's a short dipole. Everybody got me on this? Now let me show you how this simplifies problems. Trust me, you'll like this. So I'm going to erase all this. I'm going to create a problem. All right. Over here. Here's an example. I'm going to have a dipole here. It's going to be fed by a current source. And I'm gonna have I equal 2 amps here. And this will be P, by the way, not RMS. And the length of this antenna, I'm gonna make lambda over 10 exactly. The reason I'm doing that is I don't want to fool around with wavelength. So if that's lambda over 10, I got that ratio, right? Now, here's the question. I want to know at a range equal to 10,000 meters at an angle of 45 degrees. I want to know the power density here. And I want to know the electric field strength. Both are legitimate things to ask. Okay? So please watch this. We're going to do it sequentially. Everybody follow me. Here's the deal. We know the current, so we don't have to calculate the radiation resistance, right? Not in the direct sense. We're going to still use the radiation resistance. Now, when we have that, we've got the current. We're trying to find the power density up here. Y'all follow me? Now write this down. That power density in general, let me do it over here. I want to make sure everybody sees this, because this is important. And when I was in your position, when I started to see sort of the overall purpose of a lot of this, it really started to make sense. But sometimes you're in there in the weeds and you don't see why you're doing it. You really don't. All right, so gotta say one more thing. Really, there's something called gain. Don't worry about it. Gain is really an efficiency factor times directivity. And the efficiency is almost 100%, so it's almost 1 all the time. Gain is the more proper term used for what I'm going to show you. But a lot of people use directivity and gain interchangeably because the efficiency of the antenna is assumed about 100%. And by that means this, that the copper losses, you all know when you pass current through a wire, whether you like it or not, there's some resistance, and therefore there's I squared R heating. Y'all with me on this class? You can't get rid of it. But if that is small compared to the actual radiation resistance losses, then you kind of neglect it, so they use gain and directivity interchangeably. But this is the symbol for gain. The power density, now write this down. This is the power density. For any antenna, if you know the gain, is the isotropic power density. So I call it P radiation. We have to find the total power radiated by 4 pi r squared. That's what it would be if it was isotropic. Do y'all agree with that? That's no focusing from the antenna. And then we multiply it by the directivity or gain. Technically the gain, but I'm just going to multiply it by the directivity. All right? Of the antenna. Now here's the deal. For us, I gave you R, right? You agree with that, class? I said it was a short dipole by definition there. That means I know this is the directivity or the gain. You agree with that? But I don't have the radiated power, do I? I gave you the current, though. Do you remember? How would you get the power radiated here? Anyone? Well, what is power if you know current? What else do you need to know? You could say voltage, but yeah, that's right. In our case, radiation resistance. The radiation resistance has to do with the power radiated, go figure. So P rad is equal to 1/2 magnitude of I squared times R rad. I think I had it down there a second ago, but that's 1/2 I squared. Do you all see I put down I as 2 here, class? It's 2 squared times R rad. Some people are going to say, do we have to memorize R rad? No, I'll give that to you. All right? So I'm going to give it to you. Right? R rad for a short dipole is 80 pi squared L over lambda squared, right? L over lambda is what? Take a look.
1/10.
Simply 1/10 squared, right? Y'all with me? So we've got P rad. Let's get P rad. I'm gonna show you something, because this starts making it real when you're getting real numbers, you're getting a real value. So what is this gonna be? Well, I got 2 squared over 2, that's 2, right? Times 80, that's 160 pi squared divided by 100, right? 160 pi squared. 1/10 squared is really 1/100. You all agree with this, class? So that's 1.6 pi squared of watts. Y'all agree? I mean, you guys sit in the back? Okay, if I'm boring you, forgive me. Try to make this point clear. All right, now I come over here to get the average power density, because that's the first thing I asked. I give you a range and an angle, right? So I come over here, I have my power radiated, which is 1.6 pi squared. Then I divide by 4 pi over r squared, that's 10,000 or 10 to the 4th squared, right? Then multiplied by the directivity. Directivity is 1.5 or 3/2. Now, it's 3/2 or 1.5 times the sine squared of the angle. What's the sine of 45 degrees, class? 1 over square root of 2, isn't it? If we square that, we get 1/2, don't we? How many understand that, right? Are you with me, guys? Okay, so that's going to be 1/2 times 3/2. So this is 3/2 times 1/2, right there. Y'all follow me how I've got every number? That is the power density in watts per meter squared. What's the value going to be? I'm not absolutely certain, but what can we see it's going to be? Well, we've got calculators. Here, I say I got pi squared, I got 1.6. If you got a calculator, somebody you can give this to me, I'd appreciate it. Over 4, so that's 0.4. This is times 10 to the minus 8 times 3/4. And what is that? That's 0.1 pi times 10 to the minus 8. Anybody got a number for that? 0.31?
I was doing it like that.
Well, here's how I'm doing it. I got 4 times 4 is 16, right? 16 and 1.6 is 0.1. Do you agree with that?
Times 3.
And then it's going to be 0.1 times, this is 0.75, so it's 0.7, right? 0.075 times 10 to the minus 8. Or what? 8, 9, 10. I'll call it 0.75 nanowatts per meter squared. I hope I'm right. You agree with me? You're looking at me hard and cross.
A question. So 1.6 divided by 4 is what, 0.4?
No, this is 4 times 4 is 16, right? Right? 4 times 4 is 16, right?
Right.
16 into 1.6 is what? 10 into 1 is 0.1, right? 0.1 times pi, right? And, oh, I forgot the pi. That's the problem. My bad. If you got a number, go ahead.
I got 9.4 nanowatts per meter.
That sounds about 9.4 nanowatts per meter squared.
Yes, sir.
That's 0.3.
I'm sorry? Is that right or wrong?
Yes, sir.
You got it too?
Yeah.
Okay. So this is nanowatts per meter squared, 9.4. I don't care about that number. Now that's the power density. How do I get the E field? Anyway. This is power density, right? What do we know about power density? Real important. You don't have to look in your book, just think about it. Power density. How did I always get it? Propagating wave, 1/2 magnitude of E squared by eta, right? So this is the power density. I can set that equal to 1/2. Remember, I want the E field, magnitude of the E field over eta, right? And that was, I'm sorry. Could you get it? Just tell me. what-
9.4 nanowatts per meter squared.
Right? So for the E field, y'all see what I'm doing here? I asked for the E field and the power density. For the E field, I take this times this and square root of it. So I can say the magnitude of the E field would be the square root of that, 9.4 times 10 to the minus 9. You want to give me this, it'd be great too. Times 2 times 120 pi. And that will be in volts per meter. I'm trying my best to get through this without driving you nuts, but I wanted to do an example, because then you see the benefit of knowing the gain of the antenna. Once you have the radiation resistance, or really the impedance of the antenna, some antennas do have an imaginary part that you can't calculate from the radiation resistance. Once you have that, if you apply voltage, you get the current. Once you get the current, you know the radiation resistance, you get the power radiated. Once you get that, you know the gain in all antennas when you buy one. It will have the directivity / gain plots. So you will have that in front of you. It is a big selling point. What'd you get?
3.67 times 10 to the negative 3.
All right, this is the E field we got in magnitude is 3.67 times 10 to the minus 3,
2.67.
or 2.67, sorry. And that's volts per meter. Now, just to give you an idea, try to get an idea of some of the magnitude here. Usually when you deal with, the way to do business, when you're dealing with power densities in the real world, they don't do, usually, when I'm talking about standard cell phone towers, standard antennas, they don't do it watts per meter squared. They do it in something called dBm. How many have heard of that term? Did you have to do it in your labs or not?
Yes.
dBm is what? It's power, right, divided by 10 to the minus third, and then it's the log of that quantity times 10, right? Let me put that up here now, because I got a little time. So usually, here I had P average in terms of watts per meter squared. Oftentimes what they do is take P, it will be in the terms of dBm per meter squared. And this will be the power density. It will be P ab in dBm. And that's given as 10 times the log of the magnitude of the actual power density in watts per meter squared divided by 10 to the minus third. And it's this is going to be per meter squared. So the units would be dBm per meter squared. Now, what you're going to see is now the dynamic range of values is condensed. That's the idea of using dBm. So if we did this in dBm, what it would be, call it 10 to the minus 8, right? Approximately. If it's 10 to the minus 8, and we take, and we divide it by 10 to the minus 3, you have 10 to the minus 5. Do you not, class? Because 10 to the minus 5, the log of that is minus 5, right? Minus 5 times 10 is minus 50 dBm per meter squared. Y'all follow me? On your cell phones, I think just about all still, if you have a cell phone, you can look it up on the type you have, how to find out what the power density is there. And they'll show you, or receive power, one of the two. And the receive power will be in dBm. Anybody want to take a guess at what it is? Where's the threshold of what you can actually see on your phone? Anybody? Because if you want to know the strength here from a cell phone towers nearby, for whatever phone you have, you can do this. The threshold usually is about minus 90 to minus 100 dBm. When you get below that, good luck. That means you just can't pull the signal out of noise. It's just impossible. That's about the threshold, but it's kind of neat to mess around with your phones and start seeing how this stuff, how you really can tell what your cell phone strength is, what the tower strength is here. And you can go back and estimate how much total power is radiated once you know the actual directivity of that antenna. Now, last thing I'm going to say, there's one other short dipole. Just let me finish this thought. That we care about for small dipole, and that's the loop antenna. Now, this is in your book. Let me just cut to the chase. The loop antenna has the same exact directivity as this one, but it has a different radiation resistance that I'll explicitly, it's in his book, but I'll explicitly put down. And a loop antenna, a small loop antenna, centered at the origin, will look like this. And it will have a radius A, and it will have a current I. In Dr. Whitworth's book, he simply says this is a complicated thing to do to solve for the actual fields, or I should say, yeah, X, Y, Z. But if you come out as before, at a given theta for a given range, you can find both the E field and the H field. And the E field from here will be given as omega mu beta. And the way Whitworth's book does it, he likes to put omega here for some reason, I'm not sure why. I like to put ratios of perimeter or something to wavelength, but he doesn't. So for his loop antenna, the way he does it is omega mu beta, and then he puts S, where S is the surface area of the antenna, pi a squared. And he takes that and he divides it by 4 pi r squared. Or 4 pi r, pardon. And it's times the sine of theta e to the minus j beta r. However, this is in the phi direction. Now let me make this one point before I leave. That's the E field. You'll notice it's in the phi direction. You notice how this current's swirling in the phi direction? E field always is in the direction, far field, always in the direction of currents. All right, H field will be perpendicular. The H field will be that value and will simply be divided by eta. Now, I don't get hung up on this. I'm going to give you some reading to do. You'll see, I'll put the formulas up there, but they're in your book. And I'll give you a problem on that. On Friday, are you here for that quiz? On Friday, I'm going to give you a quiz on directivity. As I've shown you, I'll give you problems, so you've got problems to work from. You'll know the quiz will be similar. And power density E field from an antenna system. Got me, class? So it's like what I've done here, and I'll give you some problems to chew on so you'll be up to date. All right? But it's not going to be a,
Doesn't it pi a squared?
Say again? Who has that?
Is that pi a squared for S?
Yes.
S is just the area of the loop. If you think about the loop,